Okay, this is the third class of size of biomacromolecules. Then we will finish up this part of the lecture. So the last time we talked about the size of the protein, also the size of amino acid, and also the DNA, RNA, the size. So today we're going to combine those concepts. Also, we integrate it into the polymer systems that how we have a relationship between the proteins and polymers. So we will talk about some electrophoresis concept. So electrophoresis, in which we probably already know some of the concept in the electrophoresis, which we have, say, here we have a hydrogels. So in which hydrogel means we have a polymer network. So we can say polymer networks. And then basically you load the proteins in this position on top of the hydrogels. And then generally speaking, you add some detergent in, and typically you add some SDS, sodium dodecyl sulfate, which is providing the negative charge on the backbone of the protein. So they are basically negative charge. And then that's why we apply now the voltage in the end of the hydrogel, which is positive voltage, with provide negative voltage here, so that the negatively charged proteins start to migrate because of the voltage difference between here and here. So and then what we know, also we learn about this experiment, is that if the proteins are larger than the other, then they're migrating very slowly. And the small proteins migrating very fast. So they are migrating very fast. So at the end of the electrophoresis process, we have different band that have a different travel speed of each protein species. So this hydrolysis, the hydrogels, then this is the key component to separate each species, which has different size of the proteins that are migrating through this hydrogens. So now probably we have some relationship in size that the pores of pores of the hydrogels versus the size of the proteins might be similar or larger size in these two relationships. So let's some figuring out and considering some typical hydrogel system. Say I will have, say, polyacrylamide system, which is the polyacrylamide hydrogel, which has been using for this particular experiment. So which we structures of the monomer of the acrylamide, which is CH2, CH2, and then we got amide here. So this is monomer. But as we know that we add the APS, which is ammonium persulfate, and also timid, which is an initiator for this system. So that basically you learn in a previous biochemistry class or different classes, then make basically radical species of these structures. And then they polymerize. Just propagating the polymerase. So monomers is coming to here, and then we got the repeating unit of this acrylamide monomer are polymerized. So if I have, say, this can be polyamide chain that, because of the addition of the APS and TIMID in the presence of the acrylamide monomer. And then to make hydrogels, so what I said is networks. So network means they have to be chemically cross-linked between these chains. So such as like this connections of these individual chains. So that make hydrogels in which a lot of water molecules are in there, so making very soft and jelly-like materials in the system. So how we do it is we actually add some bis acrylamide, in which we have a bis means you have a two of this. So the bis acrylamide structures is that we have some same system. So you have CH2, CH, 2, and then we got basically the same component, but you have some additional acrylamide molecules are coming to here. Something like you have both the acrylamide, I'll do that like this, then monomers are connecting to each other. So it's a bis acrylamide. And then we basically add this to the system in the presence of acrylamide solutions. So because of which, when you add APS and TIMID in both presence, it's both presence of this and the bis acrylamide, what will happen is this becomes radicals, as I mentioned before. This also becomes radicals here. And then they co-polymerized. So become now you have, say, if this is acrylamide of the polymer, then some bis acrylamide make a bridge. But at the same time, you can also have, because of the radical process of here, they can also make a polymerization from this initiating point. So then you can make another chains here. And then during which, if the bis acrylamide still can randomly incorporate it, so they can form additional bridge, and then you can have a form of the polymerization that occurs in a very, very simultaneous way as time goes on. So when you add basically this component and the bis acrylamide component and APS and TIMID in water, and just you start these reactions, and then end up with some, after 10 or 20 minutes, you just wait and then come back. Then you have a networks of the polymers like this. So we can make hydrogels that like a jelly-like materials. So now we can think about it. And we think about some molar ratio. So let's say we think about, say, molar ratio between acrylamide versus bis acrylamide of the ratio. So say when we think about the simple cases, that 10 molecules of the monomer of the acrylamide versus 1 of the bis acrylamide. So that means in a right conditions, they make a polymerizations of using this, but if they have 10%, maybe a little bit less than 10%, but almost 10% of the probability that this bridge molecules are incorporating into the system. So that means we have say like this, this is the right monomer, but if you say 9 of this, for example, 9 of this is polymerizing. At the same time, the tenths of this, say H, like this system is so one bis acrylamide is incorporating during the polymerization of the system. So the 9 to 1, for example, well, actually it has to be 10 to 1, but it's similar, 9 to 1, for the simplest case. And then also similarly, then you have, say, this is 1, then you have also same unit of this acrylamide monomer that can be 9, can be incorporating here. Also it can be this, which is bridge molecule, can also incorporate it. And then you have another acrylamide polymerizations like this. So say, if you think about the lengths now, the lengths that we talk about in the first class of the size of the bio-macromolecules, then which we have, say, here to here, and then this the here to here is about 2 angstrom. Then each unit of this acrylamide monomer, probably 2 unit, 2 angstrom, and then times 9 of unit, then probably think this bridge to bridge, the lengths in average, probably we have 18 angstrom, which is 1.8 nanometers. Right. So remember the first class we talk about the size of the protein, which is I will give you the first example, which is lysozyme. About 140 amino acid, that we folded into the 3D dimensional space, which is cube. Then what we end up with the calculations was about some 2 point something nanometers, which is about the 6 amino acid incorporating into X and Y and Z, and then they all 140 amino acids are packed well. That is about the size of the protein, which is very similar, in which about 2 nanometer, which is a similar size about of the protein, which is compared to lysosome. So then, does it make sense? Then we have a 10 to 1 system to make this hydrogel system. Then probably this like a rectangular system. If the rectangular system, then this is the longer axis versus this is a shorter axis, but this is a smaller in size. But I think it's reasonable the size in length when a protein can go in there, probably like this size of the protein can traveling through these networks of the polymer. Okay. But this is 2-dimensional system. I mean, you think about some 3-dimensional system. When you imagine that you eat a jelly, then jelly has the hydrogel like this. It's a protein network. It's called a gelatin networks. But jelly is basically 3-dimensional structure. So you can imagine the situations in which we have the polymer chains. Whatever the polymer is, can be a gelatin, can be polyacrylamide, can be a collagen, can be polyanisopropyl-acrylamide, or whatever those things are. In this case, you have a 3-dimensional case, then we have some rectangular or network, but that is connecting to growing like this way, or behind of this whiteboard of the networks, complicated networks is formed. But also, if you think about if we add 10 to 1, the molar ratio, which is 10 molecules out of the 1 bis acrylamide molecules, but that is an ideal case that we draw like a 9 or 10 acrylamide is polymerized, but then the one which is 10% of bis-acrylamide goes integrated into the polymer chain grows. But this is the ideal case, right? I mean, it's like when you think about it, there can be, say, maybe 7 or 6 monomers has come, and also the bridge bis-acrylamide can come, and also maybe 5, 6, 7, 8, 9, 10, 11, 12, and then bis-acrylamide comes. So it's kind of random process, as I mentioned. On average, you have so many molecules in here. We have an average of sometimes 7, sometimes 10, sometimes 11, 12. That all the distributions are making this networks is more complicated than we imagine. But generally speaking, some size can be bigger, then the other size can be smaller. But it's as a distributions of on average an ideal case, that probably 9 or 10, the acrylamide monomer is polymerized, and then at which we have the bridge molecules is incorporated. But there's a distributions, 9 or 8 or 10, 11, 12. So that providing now very nice situations that say, if we think about some situations that remember was the 10 to 1, 9 acrylamide, and then 1 bis-acrylamide we provided to 1.8 nanometer in length. But they can be different, right? So 10 and 1 bis providing 2 nanometer, but 11 and then 1 bis providing about 2.2 nanometers, so on and so forth. So we have some distributions now. Then say about 1.8 nanometers of the pore. Maybe probably they are most abundant pore size in length, but they can be distributed like this way. Probably. So that means proteins larger than this, because of the distribution. If there's no distributions, then it's not possible to achieve such a resolutions, and each individual with a different size of the protein can travel different way, different speed. But because of this distribution, say when protein actually has a little bit larger size, then it has to have this pore that can penetrating to this network. So that can be slowed down because other smaller size of networks that the larger protein is difficult to travel through these polymeric networks. How about the small one? Small one has, say, penetrating easier using this pore networks. Also these networks also. At the same time also, even if they have a larger pore size through the networks, still they can travel very well. So they can, overall speed of the protein can travel through these hydrogel networks during this positive end, because I'm negatively charged to protein species, so that they can travel through this network very fast. So that's providing a different speed. During electrophoresis. That's right. This is the key. I mean, if this is the gel, the hydrogels, that's similar to the delta function. Similar to delta functions that is like 1.8 nanometer, and there's not others in the pore size, in the length of the polymer chain. It's impossible actually. Larger protein can travel. It's very, very, very difficult to travel this. But because of this distributions of the beauty of the distributions of the size in polymerization process, so it's kind of easier. Even bigger protein can travel, but it's slow, but it's possible. But the small one can travel faster. But if the small one can even smaller than this size can travel very fast. It's kind of sieve. It's like a sieve system that if the hydrogels then like this and it's bigger, it's actually never penetrating through this network, so like a sieve. But this is not a case for the hydrogel system. So that's why in practice, actually, in a real experiment, we actually use about, say, 5 to 10% of bis-acrylamide. The monomer is actually added to the system. So this ratio is also very, very, very important for providing the gel network formations. So we talk about the STS phase gel, through which the proteins are traveling. So now we talk about little bit different situations where instead of a synthetic system, we talk about some natural system, which is the agarose. Agarose is polysaccharides. The structure of the agarose you can just search easily by the Google. But the point is, instead of making the bridge, which is the case of the previous case of bis-acrylamide, which is a chemical that are during the polymerization, so you have the double point providing, and then they have a bridge role between this chain. But this natural polysaccharide has a little different mechanism, which we have, say, the polymer chains are here, which is the agarose. Then they form by the hydrogen bonding, form like networks like helical structures. So that say you have one and the other say comes like this. Then you form like wrapping to each other, for example. Wrapping to each other systems of these two chains are here. So but the thing is, not all chains are forming the networks, I should say. So which means that some chains of the agarose doesn't participate in forming the helical cross-linking, which is physical cross-linking formations. And then the other one is like this. And then in some chains, the other chain comes here, and then they form networks. And then some remaining chains are free, not forming the networks. Also say like this, and then form networks here, and coming here from networks, and then another chain comes here, forming networks. Another chain comes here, forming networks like this. So we have a different process. So of course this is hydrogen bonding system, basically. So that means you heat it up or cooling down of the temperature, then they have a different formations in the cross-linking by the helical network formations. But on average, the size of the pore much larger than the previous case, which is PAGE, polyacrylamide gel electrophoresis case. Then the pore size in this case is much larger. So that this case is for DNA electrophoresis or the RNA electrophoresis, because we mentioned in the second of the size of bio-macromolecule class, then DNA is much larger than the protein. So that actually network formations in the hydrogel, the size has to be also matter. For the DNA, it has to be bigger in pore size. Otherwise, DNA or RNA cannot penetrate and travel through this electrophoresis process. Typically, DNA RNA itself has a negative charge in the backbone because of the phosphate chain of this phosphodiester backbone. So then there's no staining process, which is the different cases that the previous the page gel system, which is we add SDS to provide a negative charge. But the DNA RNA itself has a negative charge on backbone. So there's no SDS page required in the system, so that the gel, this agarose gel, simply you add DNA or RNA that allowing travel through this by applying the voltage between these two ends. So the size of the pore, the agarose is much larger than the bisacrylamide case. And also now, these hydrogels are, generally speaking, these hydrogels are the first case is a synthetic polymer. And the second one we provided briefly was the natural polymer. So synthetic polymers actually, and this we control, in this case is control the molar ratio between the monomer and I should say cross-linker, which was the bisacrylamide case. We basically control the pore size by controlling the molar ratio between these two components. The natural polymer is a little bit different because they have, say, by this polysaccharide chain itself has a very, very larger molecule compared to synthetic one. So larger molecular weight compared to the synthetic polymer, and then also somehow they randomized. I should say randomized in the physical cross-linking. Physical cross-linking. So then it's a different process, which the natural polymers that you have some wrapping around to each other, I should say. So your one arm comes here, the other one comes here, then wrapping around to make a physical component. So this is a little bit randomized, so that it's kind of difficult to have such a high resolution, I should say, separating a little bit different molecular weight in bio-macromolecules. It's difficult to actually separating because of some randomized pore size formations in the polysaccharide case. So this is actually working for only super large macromolecule with less resolution in separations. Which means that you can basically change the 11 to 1 or 15 to 1 or 20 to 1, that making a pore size is very easily. But in this case, it's very difficult to control the pore size, so that it only works that the molecules to separate has to be itself is very large. The molecule otherwise is difficult to actually separating. So it's more, the synthetic one is actually more popular than the natural polymer hydrogel in this case. Okay, this is the end of the size of the bio-macromolecule classes. So we have 3 classes in series. Next one is we talk about the protein purification. Thank you very much.